Okay, this is related rates problem, and we're going to talk about a cone-shaped coffee filter. So the first thing, and it's going to, if it's a cone-shaped coffee filter, it's going to kind of look like this. And I'm making it big enough so we can label it. And it says it has a radius of 6 centimeters and a depth of 10 centimeters. So here's our depth of 10 centimeters. Actually, I think I'm going to put this outside, 10 centimeters. So I'm going to call this the height, and this is the radius, okay? And the water drips out of the cone through a hole at the bottom at a constant rate of 1.5 cubic centimeters per second. So what's important to look at that is to look at the actual units, centimeters per second, because that's, cubic centimeters per second, because that will kind of tell you what it is. So if it's dripping out, it's making the water is leaving there, so the rate is actually, since it's a cubic centimeters, this is a volume. So they really gave you dV dt, okay, because the volume is going to be negative 1.5 cubic centimeters per second because it's leaving the cone, so it's negative rate. And since cubic is volume and seconds is time, that gives us dV dt. They want to know we want to know how fast is the water level falling when it's 8. So they are asking for dH dt, how fast is the water level falling, okay? So, and we will have to know at the time when the height is 8, but for right now we don't have to worry about that. So we're going to look for what is the relationship between all this, and we're talking volume. So the volume formula is 1/3 pi r squared h. And because it's a cone, and this is unique to a cone and a couple other shapes, is every time the water, falls down, so I'm going to use blue here so you can see what I'm talking about. Every time the water goes down in this cone, okay, do you see what's happening? Not only is the height changing, but the radius is always changing. If I were to do this each time, you'd have a bunch of little similar right triangles. So I'm going to do a bunch of similar right triangles. So the radius is changing and the height is changing each time as the water goes down. Now that's important to know that, because what you want to do is make your formula so that, because we're looking for dH dt, is to show how the radius and the height are proportional to each other, and we're going to actually put that into the formula so that we can come up with our answer. So we're going to set up a proportion. The radius is to the height as 6 is to 10. And since we're solving for h, we're going to have our whole formula. I'm going to solve this for r, so I'm going to cross multiply 10r equals 6h. And so the radius is going to be 3/5 the height whenever it moves. We can actually take this right here and put it in the r spot now in our formula, and then now our formula will be unique to this picture and will be all in terms of the height. So it's pi, then we're going to do 3/5 h squared times the height. So the volume is going to be 1/3 pi, and then we're going to square this, so it's going to be 9/25 h squared times the height. And then we're going to continue to multiply through, so it's going to come out to be reduced down 3/25 pi h cubed. Now right here, this line right here, we haven't done any derivatives yet. We just came up with a unique formula for just this cone, okay? Just this cone. Now we're going to start doing the derivative. So I'm going to do the derivative of the volume, okay, equals, and this is the power rule, 3 times this is going to be 9/25 pi h squared, because I did the power rule, 3 times that and dropped 1, dh. And since everything is related to time, I'm going to go through and divide through by dt. Now I have a formula that talks about the rates, all right? And I know that we're going to basically be solving for dH dt. I wouldn't move everything around if you can just start plugging everything in. So this is negative 1.5 cubic centimeters per second equals 9 over 25 pi. And they wanted to know the h right here. This is where we're coming into it, when the h was 8 centimeters. So right here is 8 centimeters. So I'm going to put 8 centimeters in here and then square it, dh dt. Okay? Now when I do that, I'm basically going to take this negative 1.5 and divide it by all this, and don't forget to square the 8. And if you'll notice, this is centimeters squared, so when I divide by that, I'm going to have centimeters per second, which will be the height. And it should be negative, which it comes out to be negative, so dh dt is going to equal negative 0.0207 centimeters per second. Okay? And it should be negative because the height is decreasing when the water is dripping out of that filter. Okay, so there's a cone one. This one is about a ladder that slides along the wall, and so this is kind of interesting. This is, I took this picture from somewhere, so I'm gonna show you what all these are. This is Y, okay, and this is X. This side is X, and we're gonna call the ladder S. All right, and it's a right angle here. So it says a ladder 13 feet long, so I'm gonna label this as 13 feet. Rests against a vertical wall. If the bottom of the ladder slides away, so it's going to slide away this way from the wall at a rate of 0.5 feet per second. So I see the feet per second, and so I know this is a rate. And if it's sliding along the wall, what they just gave us was dx dt. Right? So we're going to put that right here. They told us that dx dt is going to equal 0.5 feet per second, and it's going to be positive because it's sliding away from that, and so they gave us that. Now they want to know how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 5 feet from the wall. So they basically gave us x is 5 feet. So we've got everything kind of labeled here. They want to know how fast this is sliding down the wall, so they really want us to find dy dt. Okay? So we have to look at what our relationship here is, and I see this as a right triangle, so I know that x squared with the Pythagorean theorem plus y squared equals s squared is the relationship. So I'm going to go through and do the derivative, so I have 2x dx plus 2y dy equals 2s ds, and then I'm going to go through, because everything was related to time, we're going to go through and divide it by dt. Now the first cool thing you can do, okay, is to get rid of the 2's, because everything here is, we can divide through by 2. So we have a nice formula here without the 2's. And the other thing I want you to notice is as this is sliding away here, okay, and this is sliding down the wall, the ladder is staying the same length. So really the ladder is not changing with respect to time because it's always going to be the same length. So really this is 0. Which makes this whole side 0. Even though I know that S is 13 feet, it doesn't matter because the rate of change of that ladder is nothing, so this whole side is going to be 0. So our formula actually comes out to be this: x dx dt plus y dy dt equals 0, which is a lot easier to use and to plug things in. All right? So now let's go back and put everything in. I know this x is 5 feet, so I'm going to plug that in the x spot. dx dt times 0.5 feet per second, so we know that too. But now I know I'm solving for dy dt, I know, but what's y? How am I going to find y? Well, they want to know when this is 5 feet from the wall. So right here, this is 5 feet, and you know that the ladder's 13. We can use the Pythagorean theorem again to find out what that is at that moment when this was 5 feet. So I'm going to do, okay, the y squared, which is the side, plus 5 squared equals 13 squared, okay? And that is Pythagorean triple, so I know y has to be 12 feet at that instant. So I know right at that instant when x is 5, y is 12, all right? So right there. So I can put 12 feet in my equation here. So I'm going to put plus 12 feet dy dt, and it equals 0. Now you can do however you want to do this. You can, I'm going to move this over here, so I'm going to say 12 feet dy dt and I move the other two on the other side, multiply them out, is going to be a negative 2.5 feet per second. And when I divide by 12, that's a point right there, when I divide by 12, dy dt comes out to be a negative 0.2083, and feet divided by feet per second, I mean that's feet squared per second, sorry, is going to be feet per second. And it's negative, so I'm happy because it is sliding down the wall. So that would be our answer. Okay? Now we're going to work on the angle. So we're going to be talking about this angle right here. So we're going to talk about, in the second part of the problem, is at what rate is the angle between the ladder and the ground changing. So we're talking about basically right here the ladder and the ground. So we're talking about these two sides. So if I look at that angle and I say, well, if I'm using trig functions, because that's what we're doing, we always use radians too, and you want to use what they gave you. And they gave us the ladder was 13 feet, and so that makes it for a nice problem in that respect. So let me go change this back to black. Okay, so I'm going to say the cosine of that angle theta is going to be adjacent over hypotenuse, which is the ladder. Okay, and I'm going to look at x over 13 as 1 over 13x. All right, now I want to find out at what rate is the angle changing between the ladder. So you're looking for d theta dt in this case because we call the angle theta. So I'm going to take the derivative. So the derivative of cosine is negative sine theta d theta equals, now if I do the power rule, 1 over 13 dx, and then I'm going to go through and do dt. Okay, and now I've got to solve for d theta dt. So this is what we're looking for, is how fast is the angle changing, and we called it theta, so we're going to be solving for that. So we're going to plug everything in here. So I have the sine. Well, the sine is opposite over hypotenuse, and we just told, you can't see it on the screen right here, but we just said this was 12, right? So if I did sine, that's going to be opposite over hypotenuse. You're looking at that's what this negative sine of theta is going to be, negative 12 over 13. You just put it right in that spot because that's what the sine of the angle is. And d theta dt is going to equal 1 over 13 times dx dt, and we already know what that is. That's 0.5, okay, feet per second. I'm just not going to put the units in this. And when I solve for d theta dt, when you multiply those two out, here you can multiply by negative 12 over 13 if you want, but just basically solving this, I said, well, this is going to be negative 12 over 13 d theta dt. I'm just taking baby steps here. And I know this is a half, so 113 times 1/2 is 1 over 26. And if I multiply both sides, because I can solve for d theta dt by a negative 13 over 12. Okay, this comes out to be negative 1 over 24, or a negative 0.041667 radians, and it's going to be per second because that's what the unit of time is. So that's our answer. So that's how you use angles. Well, there's two problems for related rates, and I'm going to have other videos with more.